And have you ever flown on a fighter jet?
Yes, I had the chance twice. Somehow there could be something in there. We proposed it to our industrial partners. They said, forget it. Don't spend a single hour on, let's say, investigating that. We did it anyhow.
For me, what I struggle with this concept is you're building an airport on a rail station so that you can fly perhaps to another rail station. And so the obvious question that came to me was, why?
What is your opinion on supersonic flight, and will supersonic commercial flight make a comeback?
That means I won't expect to see this on the exam.
Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour.
Hi, and welcome to another episode of On Air Actually Rocket Science, the Student Council of Aerospace and Geodesy's official podcast. My name's Killian.
And I'm Shedden.
And today we're very happy to be joined by Professor Hornung, who is the head of the Chair of Aircraft Design, as well as being the head of the Department of Aerospace and Geodesy. Thanks so much for joining us.
It's a pleasure to be here.
We'll just start off with a quick this or that to see what type of person you are. So, okay. Fixed wing or rotorcraft?
Yeah, fixed wing, clearly.
Yeah, okay, sorry. Why ask?
Garching or Ottobrunn?
Oh, that's a tough one. So I have been staying in Ottobrunn for a while. Currently in the situation Garching, but in the end, I guess Ottobrunn will be much better.
Okay.
Okay.
Hydrogen or electric?
Hydrogen.
Okay. Landed wing or truss-based wing?
Truss-based.
Subsonic or supersonic?
Okay, personally supersonic, but environmentally subsonic.
All right. SolidWorks or CATIA?
CATIA.
And then finally, tea or coffee?
Coffee.
What about you?
Tea, myself, yeah.
Oh, okay. I have to say coffee. Okay, let's start off with a little introduction. You studied at the Bundeswehr University and you got your doctorate in aeronautical engineering. You also won an award on your thesis, which was in reusable space transport systems.
Yes, right.
From 2003 to 2009, you worked in the military air division at Airbus. Mm-hmm. And 2010 is where you started at TUM and as a professor, and at the same time also began your involvement at Bauhaus.
Yes, right.
Okay, I have to say I was very intrigued to find out about your thesis on space transport systems. Can you tell us why the initial focus on space technology and why now completely shifting to aircraft design?
Yes, somehow it was combined. So just to recap a little bit, so my studies, yes, at University of the German Armed Forces down in Neubiberg, which is close to Ottobrunn. At that time, also that focus on aircraft design was already there. So also master thesis already was in that issue. Then due to my, let's say, affiliation with the armed forces, I went to normal duty to the US and then back to the university and came into the program, and they had a big, let's say, national research program running on reusable space transportation. So a lot of that was initiated from the original Sänger design, so having something which is reusable to bring down the cost for space access. So that was the main driver. A lot of activities in there, propulsion, thermal systems, and so on, because it's very, very challenging to, let's say, have the acceleration in the atmosphere still to get, let's say, easier access with a reusable vehicle. So in the end, it was a flying vehicle. So what we talked about is a kind of an aircraft type. The only thing is it's a pure acceleration vehicle. So you have to accelerate up to, Sänger was designed for Mach 6.8. And there were something like, I would say, at the three locations of Munich, Stuttgart, and Aachen. And I would say it's roughly 80 to 100 researchers working on very specific fields in that respect. And we started that approach to bring it back to the design. So bring it back into, let's say, the baseline Sanger concept. So what have the, let's say, improvements in technology over 12 years of that research program funded by DFG have brought in the, let's say, in the final design and getting closer to that target. And that was more or less the baseline for, let's say, my study. So bringing all the conceptual design tools together that formed, let's say, the baseline for Sanger in the past, where it was still, in that case, it was even Daimler-Benz Aerospace at that time when it was done. And that was part of the story. So one of the, let's say, approaches that happened was supersonic combustion ramjets, so-called scramjets, which they considered to extend the air breathing operation to higher speeds. And the question was now, does it bring a benefit or not? And that was part, let's say, of my thesis in the end, to show that having a supersonic combustion ramjet with the performance data at that time, it wouldn't bring any benefit because it's a pure accelerator. And you only design that type of propulsion system more for constant operation than really to accelerate something. So it showed that more a rocket-based one for the higher speeds is more beneficial than an air breathing configuration. So my thesis was rather showing that it does not work than that it does work. So nevertheless, for a scientific perspective, it's also valuable to show things that don't work.
All right. And were you expecting, was it your goal to win an award, or did it come by surprise?
No, it was just by surprise.
Okay.
And you cannot let's say, influence to some extent. So
Okay.
I have been also member of, let's say, the staffing of the DGLR, which is the German, let's say, association to tackle all the aerospace domains. And we also have been, let's say, doing selections of, let's say, awarded thesis work. So from student thesis up to dissertations. And you cannot judge it because you always have to get a common view. You take a look at multiple candidates. So this is nothing you can expect. So because there's always a selection. The only thing that you can do, try to do your best to be convincing, and that's it.
And so we mentioned earlier that you're both involved at the university, but also at Bauhaus Luftfahrt. What's that like, juggling those two, and how do you split up your time? What do you do for each one of those?
Okay, now it gets dangerous. So if I take the official words, I'm 1 day per week at Bauhaus Luftfahrt. Okay. So being the executive director of that, in reality, it's somehow because you have a lot of synergies, because it's not only like, let's say, being at a university is just about teaching obligation and doing your own research, but it's also a lot of coordinating and doing reviewing activities and so on. So you find a lot of synergies between both tasks on Bauhaus side as well as on TUM side. So a lot of, let's say, the appointments are with a kind of double head situation. So you can split it. So in the end, task-wise, it's somewhere split 50-50. Not with the current position as the department head on top. So let's say the fraction of Bauhaus had to shrink a little bit, right, especially in that location discussion that we are currently having. But this is roughly the share, 50-50 is somehow the target.
And so you just mentioned your involvement in the department as well. What's your vision for the next 5-10 years for the Department of Aerospace and Geodesy?
I guess we already have achieved one major step, which is to, let's say, place the new bachelor. And that was really a part of discussion that we had when we were still somehow in the mechanical engineering domain in the faculty, to tailor it a little bit more to the aerospace need, because we have some, let's say, very specific topics. The problem was always to download elements from the master to the bachelor, right? Because it was more or less a common basis, and that was part of the problem that we said, okay, one of the targets is already achieved. The problem is that now the success on the application side is so overwhelming that we are struggling to keep up with the resources. And that's one of the key elements. So the vision would be really to have an environment where we can, let's say, provide the best teaching and research activities in a kind of a modern aerospace study program. And that was also the target in that curriculum, to get some additional elements in there which you won't find in classical aerospace driven studies. And that's, from my perspective, very good. now, let's say, also on the infrastructure side, we have to deliver, because without that, it will be getting very hard.
Yeah.
And is your interest in aviation limited to design, or do you also enjoy flying?
I also enjoy flying. I have my private pilot license, the American one, because it makes it easier to sustain it. The problem is always time, because in order to, let's say, do safe flying by yourself, you have to spend the time, you have to get airborne and so on. And especially in the time when kids are still small, and you have 2 jobs in parallel, there's, let's say, limited time really to continue flying. I love it, but I just currently don't do it because I cannot guarantee, let's say, a safe state. And that's something which for me is mandatory, because it's not worthwhile to risking something.
And have you ever flown on a fighter jet?
Yes, I had the chance twice, I have to admit, which was still during my armed forces duty. So I was, let's say, appointed to go to Holloman Air Force Base in New Mexico in the United States, because we had an F4, let's say, aircraft swap out. So originally, it's the way that the Air Force pilots get basic flying training, and then they get an affiliation training on the final product. So on the German side, either it was F4 Phantom or Tornado. And in Holloman Air Force Base, there was the basic training on the F4 Phantom. And what also happened is that they have the instructor training. So a little bit Top Gun on the German side. Really the top-notch pilots to being educated as instructors, also flying in there. The problem was they were still flying on an old model, the F4E, and the German version had a lot of modifications to that. And we transferred 24 of the German ones to the US. I was let's say, the technical officer to coordinate, let's say, that transfer on site. And with that, I always looked at the airfield, because in Holloman Air Force Base, there's also the F-117 stationed. And as the F-117 is flying mainly automatically, the pilots had to get recurrent training on a modified T-38. So that's the black one that you might know from Top Gun, the first one. So the black ones are more or less the flying aircraft, the training aircraft that are located in Holloman Air Force Base for the F-117 pilot. And they always had double-seaters in there. And I just asked my American counterparts, what's necessary to get in the back seat of that? And they tried it. They didn't manage to convince the 2-star general to do it on the T-38. But instead, they proposed, okay, we have the F4 here, so why don't just take the backseat of the F4? I said, well, just tell me the time, the day.
When and where.
When and where. Which wasn't so easy in the end, because one has to consider that beside trainer aircraft, you have some functionalities in the back cockpit on an F4. In emergency case, you have to be able to handle. So it was some simulator hours before, some training, and really to get through the emergency procedures in the end. And then we had, on one day, we had a 2-ship. So I was flying with a German instructor. An American colleague was flying with an American instructor. So we had a 2-ship formation for 1.5 hours, and we were able to fly. So with handover and full control of the aircraft, it was really fun.
Any G-forces pulled?
Definitely. So you have to try it. And let's say the most surprising part is it's not about the G-force itself. It's about really to see that a 180-degree turn, if you fly at 5.5 Gs or 6 Gs, is not done in 3 seconds.
Right.
So it takes something like 30 seconds. And just to have that maneuverability and also the stress on the body to keep the blood in the head is something which is quite an experience. And also to, let's say, really get engaged into a blackout and to see how soon the body can recover from that. That was quite amazing.
So you mentioned Top Gun twice.
Yes.
So I have to ask you if you're a fan of the franchise, of the movies.
Yes. I guess they are still excellent movies, and a lot of that is really based on realistic details. Yeah. And one has to know that also Top Gun 1, especially the first movie, has been a teaching movie also for crew coordination activities are really in the basic pilot training. So there are a lot of elements in there. Some of them you have to question, but nevertheless, it's a movie in the end. But still, there are a lot of realistic elements in there, and somehow it also, if you have been flying twice in such kind of an aircraft, it somehow, let's say, brings the feeling across, and I guess that makes it quite nice.
Yeah, I mean, understandably. So we'll move to future aircraft operations in a minute, but first, I would really be interested in if we could talk about how we got to the status quo of civil aviation, the classic tube and wing configuration. It's one of the lectures that you teach that probably most aerospace students will go through. How we got to where we are right now.
I guess, let's say the basic principles, starting with the very first aircraft, even if you take Wright Flyer or whatever, let's say in getting into the complexity of interaction. So creating lift, being able to control the aircraft, have a propulsion system which is powerful and light enough in order to, let's say, get really transport performance out of an aircraft. Somehow force the natural way that we see in a tube and wing, that we try to divide the functionalities on aircraft as far as possible. So the less interaction you get, the more you can also work on technologies on improving in a stepwise, let's say, incremental approach, somehow the performance of an aircraft. And this became, let's say, quite important due to the, let's say, growth in demand on the air transportation system, because with the growth in demand, you still wanted to have maximum safety in flight. So you don't want to experiment. So you want to be sure on technologies that you bring in there. And with that, you always had a solid baseline, and you started to bring more and more technology that, let's say, brought us to the way that we could be able to cut down fuel consumption per passenger in 100 kilometer by more than 80% over the last 8 decades. So it's really that incremental step-by-step improvement to make it work. And one of the enablers was that functional breakdown that we see in a classical tube and wing configuration. Yeah. Now we are leveling off to some extent. So either we find additional elements that might be now pay off, and this is always what we have to keep in mind. We haven't employed all the technologies at hand up to now in the aircraft, because they all had to be economically viable. So you always have to see, okay, what is the additional effort to bring the technology into production? So what is the rise also in the cost of the aircraft versus the, let's say, cost reduction you get in operation due to reduced fuel burn? When fuel was still cheap, it's a different economic balance for some of the technologies that they want to apply and others not. And now talking about sustainability, we are somehow forced to get with new sustainable energy carriers, which most likely will be more expensive. So we are talking about SAF, so sustainable aviation fuels, costing 2 to 3 times what kerosene is costing. Right. So it will shift the threshold. And now this is currently the challenge. Is there something that is still in the drawers that we now could be able to apply and still show an economic benefit?
Right. And so I think another part of what I really enjoyed in your aircraft design lecture was that you learned things that you would never really think about. And so I think for me, one of the things that I really liked, and maybe that you could explain, is the shape of the wings, let's say on a classic civil aviation aircraft. Why do we see this downward sweep, as we call it, for that type of aircraft? Or backward
the backward sweep. Yeah, it's just in order. So let's say the target is really to get maximum transport performance. And that's always, let's say, a relation between the amount of passenger that you bring on the aircraft and also the flight speed. So because if you increase the flight speed, the flight time is reduced. So an airline can use the aircraft on multiple turns over the day. And so this is providing economic benefit for the airline. And in order to, let's say, to push the speed limit, the sweep is one of the features. So by putting more sweep on an aircraft, you can, let's say, delay some of the effects that we would see in that transonic regime. So going from subsonic to supersonic condition, especially if we have supersonic flow, we have, let's say, dedicated flow phenomena which will increase drag. So wave drag is one of the, let's say, pressure drag elements that has a drastic increase in the transonic regime. And with that, you can reduce a lot of those effects. And we can also see that we can increase further the speed. And this is what we see today. So all the long-range aircraft are flying at around Mach 0.85. And that gives maximum efficiency also for the air transport system because everybody is flying at the same speed. Right. So you find also the same characteristic on the aircraft.
Right. And for me, another interesting thing that, for example, we don't see on this A300 in front of us, you were mentioning efficiency before. What role does a winglet play in bringing that efficiency to a better place?
Typically, so what you're having, the more slender the wing gets, the more distributed the lift is generated. That also gives you an indication about the impulse that the flow will see behind the wing. So with that impulse, what you are creating a turbulence in the flow. So this is what is, let's say, seen as the big vortex behind a wing that is created, which in the end also forms what we see in a contrail. But this is just about the condension being, let's say, captured in that vortex. And the idea is to spread that lift distribution as far as possible. Nevertheless, we have limitations in span because we have standards for airports. So we have dedicated classes. So the target is now, what can you do in order to spread it further? And winglet is one of the options, where you on the one hand side just continue with the pressure distribution along the curvature of the winglet, and by that spreading that impulse that you bring in there, and the average amount of impulse is reduced in that case. And with reducing that, you also reduce the lift-induced drag. So this is one of the elements. And the second one, if you do especially modifications to an existing aircraft, you can use larger winglets in order to also use that, let's say, pressure equalization around the wingtip to create an active force which is pointing forwards on the winglet, which helps you to reduce drag. And this is something which you can tailor, but in most of the cases on the original design, like you see it, for example, on an A350, or on a 787, they can work with very small devices because you do the basic design purely that it's optimum. Mm-hmm. But in order to get enhancements, and this is what we see on most of the short medium range aircraft, they have grown their capability over time. So you have to adopt the shape, the aerodynamics of the aircraft, but you don't want to do a complete new wing design because a new wing design doesn't mean a complete new development of the aircraft. So this is one of the levers that you can take.
And another thing I find really interesting about the design, let's say, the underlying concept behind civil structures is the need for passive stability. The fact that a gust will not blow the airplane into an unstable position.
Yes.
What are some aspects in the design that people who perhaps don't study this craft that would not know about? So I'm thinking like dihedral in the wings, such things that help to bring that stability back.
There are a lot of, let's say, different aspects that you have to consider, but I would rather address it from a different perspective. One has to consider whatever we see on an aircraft is a big compromise,
right?
Because you have a lot of, let's say, different factors affecting it. So if we start with a very simple one, just that two types of configurations where we have the engine under the wing compared to having the engine at the tail. Where you say, okay, it's purely just moving the engine from one position to the other. No, but the consequence on the aircraft is quite severe because if you're moving the engine, you are moving the system with the highest single mass on the aircraft, which will have an influence of the center of gravity of the configuration. And is you have to have a dedicated allocation of the wing with respect to the center of gravity. If the center of gravity moves back, you also have to move the wing back. And now you come to a situation that now the forward fuselage is getting longer than the rearward fuselage or in the previous configuration. So also instability on directional control gets less because you now get more destabilizing surface in front of the wing and in front of the center of gravity. So you have to compensate it with a tail again, which at the same time did get a smaller lever arm. So you have, let's say, a double penalty on the tail that you have to consider. And with a bigger tail, in order to compensate for that, you now face the situation you have more drag, and more drag on the configuration means more thrust, so bigger engine. And so you see, it's a kind of a coupling where you always have to consider what are the consequences you do that. And this is why I also find aircraft design so fascinating, because it's finding that best compromise, because there is no single silver bullet to get the best design, also not technology-wise.
So you have all these teams coming together and trying to figure out what that optimum point is. I know everyone's professional and everything, but do you ever get to the point where there's a certain department that goes, we need to have this for this plane to work, or people are trying to move the point of compromise to where it fits them best?
Yeah, this is exactly the reason why you have something like, let's say, conceptual design departments in there, because you need to have a small team trying to figure out, let's say, what the best compromise, first of all, is before you get into maturing or getting into the details of the individual components. And one of the examples, and we have quite frequently discussed that also with Airbus colleagues. So just to give an example, so as long as you have in your development organization a team which is dedicated to, let's say, having a wing box, the best wing box design, how likely will it be if you would have the full, let's say, engineering development teams develop the next generation of configuration, that this configuration will be without a wing box?
Right.
So it's a little bit, you have to somehow insert changes, and that might even have an influence on the structure of the organization, because in the end, it's somehow represented in the functionalities how to do that. But this is just one example. So it's also addressing other aspects in there. So as we are discussing, let's say, more radical energy carriers, and one of the typical example was that electrification. To be honest, I said it at the very beginning that I would go for hydrogen. Yes, due to one reason, because we don't see the battery technology at hand that would allow us to go full electric. If we could go battery electric, that would be the best that we could do on an airframe. But battery technology is not there.
Right.
And we will see if we will manage to get there, but you have to find that compromise. And in a battery electric system looks completely different to something that we see today. So you have to adopt also the organization, and also this is something which is currently happening in the industrial baseline, that also players change. So there are no new players in there. But nevertheless, the problem is if you now start with electric systems, to get it into product and you get the return on an investment will be somewhere around 2035, 2040.
Right.
You have to have some very good financial backing in order to survive that.
And so that's about the status quo that's today. Then let's move on to Bauhaus Luftfahrt, who are very much looking forward to the future. Bauhaus Luftfahrt is a think tank. What exactly does that mean?
Yeah, think tank doesn't mean, so we are rather considering ourselves as some kind of, let's say, strategic technology assessment. So what we are mainly looking into is what kind of, let's say, technology is currently showing up at basic research. So you look at fundamental research, there are some key developments, and what you try to translate is if this is now showing an increment. And just to, let's say, get one or two examples, if you take, for example, the fuel cell efficiency. So it was quite a long time, PEM fuel cells were known, but the, let's say, power density of the fuel cell weren't that good. So, but there were changes in the setup, changes in the material. So you have seen a kind of, let's say, of a jump in power density. And now the question is, was that jump sufficient to now make it work on an aircraft? And another aspect, for example, and we tested that quite thoroughly, is there are so-called thermal electrical generators. So it's a crystal. If you put, let's say, heat on them, they're able to generate electricity. And there was a figure which identified the efficiency, how heat can be transferred to electricity. And in basic research, there was, let's say, a jump in that factor. And so the question came up, okay, is that jump now sufficient to provide a contribution to an aircraft? So we did an initial investigation about what is the basic principle, how does it work, how can it be integrated, and then ended up in the end even in a joint LUFO project, so even with engine manufacturers and so on board, to do a full-fledged, let's say, study on using the waste heat of an engine to replace the generator. So this is the kind of trigger that we try to give. And this is why we have also a wide spectrum of disciplines at Bauhaus. A lot of them have no aviation background at all. So they come from a dedicated area of research. So they have the capability to understand basic fundamental research results that you will find in publications, and the possibility now, together with the engineers, to transfer it to something which is an application case for an aircraft. And this is the way we tackle it. And also what we are doing is we are somehow, let's say, questioning the status quo. So another example, going back to electric, there was already, even before I started at Bauhaus Luftfahrt, so they looked into some of the basic technologies in that technology radar monitoring. So they have seen energy densities, power densities of electric motors, generators went up, battery energy densities went up. Is there something on that? Is there something, is there potential in that battery electric? So what we did say, okay, 2011, we had enough figures to say, okay, we did an initial assessment on a regional aircraft. Somehow there could be something in there. We proposed it to our industrial partners. They said, forget it. Don't spend a single hour on, let's say, investigating that. We did it anyhow. So we wrapped the full team at that time, roughly 28 researchers together, 4-month duration, do a kind of initial feasibility study. What would it look like? What would it mean if you would go to a full battery electric 190-seater aircraft being capable to somehow replace a majority of A320? And there was no general showstopper in there. So in general, it could work, depending that the individual systems provide enough efficiency, and one of the bottlenecks is the battery. And from there, and a lot of activity started then in parallel, we have seen a lot of discussion now, and now a lot of, especially on the smaller aircraft, are looking into hybrid electric. So this is a little bit of what we're doing, and we have been doing that also for other fields. It's really to test it and to have ideas, to bring it together, to test it. And again, a little bit to jump back to what my PhD thesis was. A lot of the ideas get discarded. It's not all winners.
Right.
Mm-hmm.
But the value of, let's say, gaining knowledge by assessing that, this is also what brings the value to the industrial partners. And that's one of the unique features. So that's one of the, let's say, very rare private-public partnership research organizations where we get public funding as well as direct support on our basic funding from industrial partners, because they say for them it's very important to have that initial testing of technologies if there is anything worthwhile to be followed on.
I was going to ask this question a bit later on, but I feel like it's relevant now. With novel ideas or unconventional designs, how do you know if it's worth investing the time in it?
Yeah, you have to bring in, let's say, a good engineering gut feeling from, let's say, all the different players. So we have quite some experienced people also on board. And that's part of the discussion. It's also kind of the group dynamic. So if you have multiple disciplines, and that's always why it's very interesting to see, for example, a physician looking into an aircraft design problem who has no idea about the aircraft design principles, but they're raising some questions. And they're raising also some questions how we tackle typical problems. And in the end, the only thing that you can say, okay, based on our experience, on our knowledge, on our, let's say, somehow still gut feeling, there's something in there. Let's test it. Let's go in there. Let's try to figure out if there is something. If there is, that's fine. This is how innovation starts. If not, okay, next one.
And are there any moments where you initially think that it is worth investment and time, but then later on perhaps a showstopper appears?
especially, let's say, looking at electrification. So once we figured out battery electric won't work for large aircraft due to, let's say, battery capabilities, there was the natural step. Everybody said, okay, then it's hybrid electric like on a car. But hybrid electric on an aircraft doesn't work. Because you pay so much penalty weight-wise by putting multiple systems on board of the aircraft, that the only thing that you can get is probably, especially for very small aircraft, like regional aircraft, you could get the possibility during takeoff and landing, so while you're very close to the ground, to fly full electric and do the rest hybrid. But the penalty is always that you will have a heavier aircraft. Yeah. And you will, in total, if you also take the electrical energy that you need for that, you will always have a higher energy demand per passenger kilometer. So there's almost no hybrid electric configuration that brings a significant benefit. The only things where it does work to some extent is where you can use that electrical system to enhance something which was a penalty before. So one of the examples in that case is the kind of propulsive fuselage. So where you put an additional fan at the rear of the fuselage, which you power with electrical energy, that you can reduce some of the drag of the aircraft by doing that. But again, we are just talking about, let's say, rather single-digit fuel burn reductions. It's not a massive game changer. It's on a similar range like other technologies that we also have on the aircraft. So there was one really hard lessons learned, to go through all the architectures and to figure out hybrid electric does work on the ground perfectly, but not on an aircraft.
Okay. And how many projects or concepts that you've worked on have we not seen yet due to showstoppers appearing and them not working?
Wow, that's always hard, because normally if you work on very early, let's say, conceptual design, and I would call that all conceptual studies, normally the ratio of the initial start to what you further continue is somewhere 100 out of 100 general ideas. Normally something like 10 will further progressed, and if you have one convincing out of that would be good. So they are quite high numbers, which you have to disregard and look into other domains.
Okay, all right. Maybe shifting back to the projects at Bauhaus, let's take a deeper look into some of the main projects. One of them is the CE liner. Can you tell us more about that?
The CE liner was exactly that feasibility study that we did on full electric. So that was exactly what I explained before.
Oh, okay, perfect. And I had a question about the CE liner. Why the C-shaped wings?
The C-shaped wings are, let's say, a consequence out of two effects. So the first one is what I indicated before. So if you go electric, the aircraft gets heavier. So even in that case, we took a battery energy density at around 2 kilowatt hours per kilogram. So just as reference, we are talking currently 200 watt hours per kilogram, so a factor of 10 in there. Still, the aircraft was 50% more heavy than a comparable conventional aircraft. So with having 50% more weight, you normally need 50% larger wing. Mm-hmm. But in order to replace an A320, you still have to stick within 36 meters of span. Right. Due to airport operation. Yeah. So you cannot just increase the span also in the same ratio. So one of the possibility was to get that C-shaped wing in order to have enough wing area to be able to compensate the 50% of the lift. Let's say the synergy with that C-wing was that the upper part of the wing was so far aft that we could eliminate to a large fraction the horizontal tail, because the engines were anyhow in the back. You need quite large pylons, which can use also to do pitch control of the aircraft. And in addition, you have the rear part of the C-wing, which was, anyhow, it was just a side effect. It was just about, let's say, a consequent out of, let's say, the increase in weight, where you have to consider how do you do that still keeping 36 meters in span.
Did you ever consider for the CE liner then, because of, let's say, part of it was the airport restrictions, yes, the concept of the foldable wings, like we're seeing the extendable wings that can extend once you've left the, let's say, the
Not for that size, because in that case, let's say the size of the wing would have to be substantially larger. So this is also not the kind of dimension that we currently see. And again, in that case, you have to trade what is, let's say, the weight of the folding mechanisms, especially if you have to increase something like 50% in span. That will be a different order of magnitude.
Okay, so another project at Bauhaus is HiShare. Am I saying that correctly?
Yes.
Yes. Okay, perfect. So can you give us a brief overview on HiShare?
Yeah, HiShare was, let's say, created out of, let's say, a discussion where we looked into the data of, let's say, long-range traveling. And in that case, a little bit, let's say, getting away from a pure airline perspective, because the airline does, let's say, in their network an A to B connection to some extent. But we rather looked into what the passengers are doing. And what we came up with is that if you take long-range traveling, it's just about 32% of all long-range travel which use direct flights. So it's 68% using transition flights, although for half of that, there are direct flights available. Which everybody knows, if you do a booking, a non-stop flight is always more expensive than any kind of stopover flight. But nevertheless, if you dig a little bit more deeper into that, what you see, and if you take the individual travel behavior, the majority, which means 68%, are flying detours. They're flying detours because any stopover is not always in the direct line which you want to go on a non-stop flight. So looking into that, we said, okay, if the majority is using stopover flights, what if we would do non-stop flights and let the long-range aircraft fly slower? Because there was always a no-go, because everybody said, okay, you don't want to be on a long-range trip on a slower aircraft, spend more time in the aircraft. But if you take a passenger perspective, you can reduce the speed of the aircraft. Still, your travel time in total would be decreased. So you would have two effects. So you're avoiding the detours. You are reducing the fuel burn per aircraft, and to bring it down to that level. So the only thing that we said, okay, if you do that, you still have on the individual flight leg, you have to spend more time on the aircraft. So would it be an option to, let's say, give a kind of, let's say, return to the passenger to give them a little bit more space in the aircraft and provide additional services on board of the aircraft? And that figured out to be, let's say, a good synergistic approach if you even assess or consider being a hydrogen long-range aircraft. Because if you want to use hydrogen on a long-range aircraft, you have to build in quite large tanks. And hydrogen has very high volume, so you can no longer put it in the wing. So you rather put spherical tanks inside of the fuselage. So that came to the situation, if you even consider, let's say, the size of the passenger amount of an A330, you would end up at a fuselage size of an A380. So you would have a 3-deck configuration, you would have a hydrogen tank in the front and in the back, and now you have a third deck. And could you use that third deck to provide additional services on board of the aircraft, to have something like a rest area, a restaurant, or whatever, so where you have additional paying services also on board of the aircraft, and give you a little bit more, let's say, things you can do while being a longer time on board of the aircraft. So we really try to bring things together. We're getting a more thorough look into what long-range travel it could make and what are the key levers that we could still employ, but we haven't done up to now because due to the, let's say, the existing system, because it doesn't allow for that.
Okay, and you mentioned that the fuel for this idea is hydrogen.
Yes.
How are we supposed to deal with hydrogen leaks or storing hydrogen? How is that supposed to work?
That's the tricky situation, and this is still what is currently investigated. So hydrogen itself is not new. So in order to handle that, there are, let's say, a lot of experiences also what you can do in order to handle it. But nevertheless, the question always to put it into an aircraft is to have the safe operation and still have the lowest weight penalty and also the lowest rest of the penalties, which also means drag increase and so on. So this is rather the challenging part in there. So the refueling and so on, that can all be solved, but can it be solved that it's still efficient in a way that you don't blow up the weight of the aircraft and so on? This is more the critical one. Whereas we have to keep in mind, we are not digging too much into the details how to do it. But for us, it's rather a platform to, let's say, try to analyze the impact. Does it have a benefit or not? And for us, hydrogen is something, it's valid to be investigated anyhow, because even if we take the other option, which would be sustainable aviation fuel, you always need hydrogen for that. So hydrogen will be in the pipeline in the new energy sources anyhow. And the question is, can we get another benefit? And one of the key benefits, if you use hydrogen, is that you don't have CO2 emissions, but you have water vapor.
Right. Yeah. And I mean, as I learned in one of your lectures, actually water vapor is, people always talk about CO2, but the water vapor, maybe do you want to go into what that actually means, why the water vapor is a problem?
Yeah, you always, if you have a combustion process, you will create water vapor. So this is a normally typical case. The topic is in combination with fine particles in the atmosphere, but also created by the engine in the combustion process, you will form condensation. And depending on the actual temperature, humidity in the air, that condensation will form ice crystals. And when the ice crystals stay for a longer time, that will have a climate impact. So especially during the night, if you have ice crystals staying in the higher atmosphere, you would have, let's say, the radiation coming from the Earth to the space would be reflected, so it keeps the heat inside of the atmosphere. So it's a kind of heating effect. And this is quite massively on a single flight. This is also what is now the issue, because what DLR in a lot of test campaigns did find out, it's just about a single-digit number of flights, so in percentage of all the flights, that are responsible for that. And this now opens up for us the pathway. Can you do something operationally to avoid to fly in that areas and so on? And that's something where, let's say, that climate impact on water can be reduced. And also jumping back to the hydrogen aircraft, if you even do hydrogen combustion, it's very likely that you'll have less particles generated in the combustion process. So also, even if you have more water vapor, it's not clear that it will directly increase the climate impact, as you are not forming more clouds. So this is still where there's really ongoing research, but this is something where also our, let's say, the partner DLR really, they are at the forefront of research showing the benefits.
The final project we want to talk about from Bauhaus is the center station. Mm-hmm. I want to see if my interpretation of it is correct. You, on top of central stations, rail stations, where you have these long stretches, you want to put an airport on top of that to be able to better connect urban areas. Is that a good representation, or is there something that I'm missing?
No, in the baseline, it's exactly that. Mm-hmm. So Center Station was originating from a cooperation that we did with Airbus Strategy. So their target was to better understand what is happening, let's say, beyond and in front of the, let's say, entry on the airport. So you have a lot of, especially on short-haul flights, you have a lot of, let's say, time penalty happening in the intermodal segments before. So there was an investigation done, and one of the ideas, and it was coming from a student from the Glasgow School of Arts. So they had students working on different concepts, ideas, and how to improve it and so on. And one of the ideas was really to bring the airport back to the city centers, where they have vanished over time. So they were much closer, but in the meantime, due to the amount of operation, they moved out of the cities. But nevertheless, what we do see, the cities are growing and growing. So the distance and therefore the time penalty to get to the airport is getting more and more. So this is where we lose competitive advantage also with respect to rail and so on. So the question was, is there something that we can do differently? And there was that idea to say, okay, can we utilize the space inside of the city? Especially if you have, let's say, city-to-city connections, typically you have the passengers and the demand more in the core of the city. So there was the idea, okay, let's take a look at that. And what they did, and a couple of students did that, and really did take a look at Google Maps and say, okay, well, what's there?
Right.
And what came up is one phenomenon that we see in most of the cities worldwide. So you have a railway system in there, which due to, let's say, how a railway is working, you have quite long segments which are straight. And also especially in the city center where you have the stations, you also have wide track systems because you have multiple tracks in parallel. And the question was, okay, is that sufficient to house a runway on top? And that was the general idea. And then there was the investigation, okay, what about the dimensions that you can utilize on most of the major cities worldwide? And it came up to it has to be somewhere around 680 meters in that domain, and roughly 80, 90 meters is the maximum width that you could have. And then there was let's say, the design of an airport around that, which became clear it can no longer be an horizontal one with all the processes, but it has to be a vertical one. So you have to put the runway on top. And then you have the aircraft handling one deck below that. Then you have the passenger handling one deck below that one. So you got a vertical structure of an airport. And just to see, okay, is there anything in general that would be a bottleneck not to do it? And most of the technologies that you will find to enable something like that is existing. So you have aircraft lifts on aircraft carriers, so they are operating 20 tons plus, so that's not an issue. You have runway systems, you have also safety systems, which also apply on aircraft carriers. So you have arresting hooks, you have nets in order to ensure that even if you have, let's say, a problem during takeoff and landing, that you guarantee that they don't fall off the building. And so on. So there was no real bottleneck in there, but it's a different kind of, let's say, of operation. And the big benefit is if you put it on the railway, especially on a railway station, you have direct access to public transportation.
Right.
So the intermodal element is quite good. The only limitation that you get, it will be most likely limited to aircraft sizes around 40, 60 passengers. So this is something that you have to consider. But still, if you take one single airport, it would still be able to handle roughly 10 million passengers per year. And that's quite significant. And let's say the advantage also coming with that is if you're offloading the classical airports from that city-to-city connection, you can free some slots in order to, let's say, serve more the long-range traveling, which has to rely on, let's say, the large airport infrastructure and therefore capture more of, let's say, the demand in the future by shifting that. But you would create a second parallel system in order to operate those smaller aircraft more on a city-to-city basis.
And so, as you mentioned, smaller aircraft. And what's interesting about this project is that it's an infrastructure project in the sense of you have to build a structure, yes, but also it comes with a City Bird, which is another aircraft. What, when designing it, what had to be different about the City Bird? Obviously, shorter runway, things like that, that conventional aircraft do not currently do.
Yeah, the key element was really to have, let's say, the flight capability to tackle the short runway. So you have to work with higher climb gradients and so on. So it's rather that side of that. The second effect is simply you have to also consider noise.
Yeah.
So can we take the advantage of the next generations of aircraft engines, to reduce noise levels? But again, this was just about a side effect. So it was not the target to get, let's say, a detailed design of a City Bird. It's just about, in general, is there something which could form a showstopper? And there was nothing really coming up like that. And it's just about one of the topics that was one of the side results, and we tested a new engine type in there. And that engine type has, while it has a much better fuel burn, a likely slightly increased NOx level. And if you now compare the NOx generation inside of the city, that could become a critical topic. And that came up out of the study as well. So NOx can be very tricky in that operation closer to the city, where we said in the end, okay, this could be one of the application cases where hybrid electric could have a benefit. Not fuel burn wise, but to have, let's say, full electric operation from the runway to cruise altitude and downwards. But that's it. But we did not do an investigation really how that would look like.
So for me, what I struggle with this concept is you're building an airport on a rail station so that you can fly perhaps to another rail station. And so the obvious question that came to me was, why, when we can perhaps improve the rail that's supposed to be going underneath that airport, is there really that much of an advantage that we just can't just take the train that's going underneath?
The topic is always, we always have to, let's say, differentiate between the regions worldwide. Mm-hmm. It's not like in every region of the world, let's say the railways network is established like that one that we see in Europe. And this is something where you also, even on short distances, might have, let's say, limitations in there not to be able to connect it. So if you take, for example, Indonesia Pacific region, you might have a lot of, let's say, short leg combinations, even on mega cities, where you won't be able to just build a railway.
Right.
So this is also something that we need to consider.
So perhaps less of the European-centric model and more of... Okay.
And it was also one of the idea, really, if we have to offload capacity from the existing system, it could be one option.
Okay.
So it's just about, it's nothing where we can say, okay, in general, it's an absolute no-go. No, it's just one option, and we just have to keep that in mind.
Okay, speaking of futuristic concepts, urban air mobility is a very exciting topic. What are the challenges in accomplishing this concept?
The core challenge is, while everybody is concentrating on the air vehicle right now, so everybody is using electrification of the system in order to make, let's say, a more easy and better, let's say, solution than a helicopter, because urban air mobility has been in operation. So they used helicopters to do air transportation services with vertical takeoff and landing and so on. So that has been in place for decades now. So you can buy that even today on Uber. If you go to New York, you can book a flight. But it's quite expensive. So the target is can we get with electrification to a cheaper model so that we have more share in that segment? The core element with that is, if you take the single flight or just the aircraft, that's simple. But as we talked about, let's say, city operation before, if you want to make use on a short one, and that's why it's called urban air mobility, it was considered to be supplementing the ground transportation inside of the city. The only thing that you have to do is you have to get airborne. So you have to spend much more power and energy to get to your cruise altitude to fly to another destination, but you don't need a ground infrastructure except for the vertiports. But the vertiports are more than just a helipad. So you need, in order to have enough throughput to really have a significant share in there, you have to have the helipad itself for takeoff and landing. And then you still have gates around that. So the footprint gets bigger. So really to implement it, you have to find the space to build that kind of vertiports inside of the city in order to get the operation. And let's say the efficiency, so the gain in, let's say, transport time by higher speed of an air vehicle compared to what is happening on the ground. And that's always the congestion example, which in the end, we are talking about different capacities in the system, is better the more vertiports you have in the city. But how much space do you have in a city to build a vertiport?
Right.
Mm-hmm.
So that's one of the limiting factors. So you really have to match that. And the problem is, if you have just sparsely populated vertiports inside of the city, the penalty of getting to the vertiport and your last mile to your final destination is eating up all the time benefit from a higher fly speed. So what came up, and we did it also TUM and Bauhaus together in a modeling of complete Bavaria to do an assessment based on mobility parameters. So putting just on the mobility simulation that you have on ground one UAM level as an additional mode on top of that, it came to that point in the best case. If you would bring the cost down to the same level as on a taxiway level, so something like €2 per passenger kilometer, you could get about the same share as taxi services. So like 1 to 2% of the transport capacity. That would be the best case. It's getting more interesting if you connect regional to the city. So more interesting places around the city where you have not the best ground infrastructure connection, transportation-wise. This is where you could gain a slightly higher benefit from the higher speed with more distance, where you could gain up to something like 3 to 4% of the traffic share in there. And especially that operation, so to get a system working is the key bottleneck. And with the system also comes the noise. Because if you put more vertiports, you now bring noise into a domain where it's normally not in. And this is something that is often forgotten. So if we got noise inside of the city, it's mainly in the street. So it's down in the valleys between the houses. And now you bring an additional noise source up in altitude. So you get a different noise impact while you operate in the city. And this is something which is crucial.
So for me, one of the challenges in UAM and the implementation of a UAM that you mentioned during a lecture once was the public perception, politics and public perception. How big of a challenge is that really?
It's a big one. So we already see it. Let's say there's a lot of discussion about helicopter operation, even around hospitals. So you have a critical service that you're providing for everybody who is in need of that. Still, there's discussion about, let's say, the acceptance of regular helicopter flights around hospitals. Yeah. So you always see it's something where you have a very personal perception of something which you might not use, but you take the penalty of it. And this is something also on urban air mobility that could be an issue if it just will stay limited to, let's say, those groups of population that are paying for it and can pay for it. And still the rest has to, let's say, take the burden. Yeah. It's very unlikely that the acceptance will be there. The other one is what we are currently seeing, and this is where we will, I guess, we'll see a gain of, let's say, experience in that, is cargo drones. So there's, let's say, an increasing, interest in using cargo drones, also in urban environments and so on. And this is where, on a smaller scale, we currently see the testing. So this is also probably something that we are currently also doing at the chair. So looking into modeling the noise, drones, as well as UAM, and to see what is the impact. What really is the noise impact along a flight track? Because you always have, again, that compromise. You can have, let's say, a higher flight altitude to get the noise source away from the people, but you have to use more energy to get to the altitude and to do your flight. So you would rather fly lower, but then you have the noise impact. And this is what we try to balance. And that's one of the very tricky things in there.
And beyond the noise research, does your chair go further in the topic of drone delivery? What the design of drones and such things? Or
yeah, what we have done now over the last 6 years, 7 years, really look into, let's say, EVTOL configurations, especially for the smaller segment. So ranging from something like 5 kilograms. So the biggest designs were around 300 kilogram. So where we also have teamed up with one of the major, let's say, industrial players on the market right now, which is Auto Robotics. So where we have done a joint, let's say, design study for them to come up what is the best configuration in that segment to have, let's say, vertical flight capability, still having a very high performance in long duration, long distances at high speeds, which is always a tricky one, because if you want to go vertically, you have to optimize for that vertical flight, and you will never get good performance in high cruise speeds. So you always have to find what is the best match. And we did a lot of, let's say, conceptual studies. We also have some operational vehicle as test specimen currently in operation, really to further understand where there's still, let's say, optimization potential in there.
And I'm also curious with topics like this, how much are you working with other chairs at the university?
We are in close cooperation. So the closest cooperation in the past has always been with Florian Holzapfel. So they have been doing a lot of, let's say, the flight control side of projects that we have been doing. So starting very early with our, let's say, we have built a drone quite shortly after I joined TUM in order to test avionics, to test sensors and so on. Florian's team has built the flight controller, the autopilot for that. Then we had a big joint research program with Airbus, getting a scaled UCAV demonstrator flying. So we did a lot of the propulsion integration and airframe design. He did, again, flight control, automation in there. So there's a very close link, which is beneficial that we are sitting on the same floor. Still, there's also cooperation with other topics. So especially on the structure side, also with Klaus Drexler, some of the elements now in the UAM or drone part, also with Ilka Javrochuk or Manfred Hayek before. So there's always, depending on the topics, a quite high exchange.
All right. Okay. So you mentioned that you like supersonic flight, and I'm sure you're familiar with the X-59. And for the listeners who might have not heard of it, it is an experimental low-boom supersonic plane being developed for NASA. And so the last supersonic commercial aircraft was Concorde, and it stopped operating over 20 years ago because of, noise, and it was very expensive to operate. And I wanted to ask you, what is your opinion on supersonic flight, and will supersonic commercial flight make a comeback?
So in general, if we take the Concorde example, so what was the let's say the reason for the final termination? So there was that heavy accident in Paris, where a metal part, let's say, tore a hole into the tank structure, so the aircraft got in flames. And so they tried to find a solution afterwards in order to, let's say, somehow seal the tanks and to avoid that something like that would happen. The key topic, if you fly supersonic, is you have to overcome the additional drag. So there's one component, which is the wave drag. So the part of the drag, the pressure drag, that is just occurring if you are flying fast, which in order to minimize that, you have to build very slender configurations. So this is also what we have seen on Concorde. It's a very small diameter, very lengthy aircraft, which we also now see on the X-59, which is one of the key elements to get it a very tiny long nose in order to reduce that pressure jump, which means decreasing the shock intensity, which allows you to fly supersonic also above land, which was one of the limitations of Concorde. So Concorde was only allowed to fly supersonic above the ocean, because that shock wave coming from that flying supersonic results in a pressure increase. And if you have a large configuration, that pressure increment becomes very large. So it can even destroy windows of buildings and so on. So you get a disturbance, but it can also cause damage if you get bigger. And that's one of the activities that NASA has been doing for decades now, really, is there a solution to, let's say, dampen that shock? So by instead of having it concentrated, getting it more diffused. And with getting it more diffused, you have less of an impact or a jump in pressure, and that helps you and could even allow to fly above the land. The key element still stays the same, that you have to overcome higher drag. So the fuel burn in any kind of configuration will be significantly higher. Mm-hmm. Especially as you have to still build slender configuration, the amount of passengers compared to the size of the aircraft is still very limited. So if you bring it down to, let's say, fuel consumption per passenger kilometer, we are orders of magnitude higher. And that will still stay the same. And there's a second effect to that. Whenever you fly supersonic, you have to increase your optimum cruise altitude. So you will no longer stay at 11 to 13 kilometers like you do it for a subsonic aircraft, but you have to rather go for 18, 19, 20 kilometers altitude. The problem is that's the altitude where we have our ozone layer most of the time. And one of the things that is not very good for the ozone layer is by deploying water vapor, and in that case, ice crystals at that altitude, beside additional effects that do happen. So from an environmental perspective, you have, let's say, two massive components that, let's say, argue against supersonic flight. It's really the higher fuel burn per passenger kilometer and also the flight altitude with direct impact, which is not climate, but it's ozone layer related. So in the current discussion and what we do currently see, I would consider, let's say, the viability of that concept in a broader sense, not for single business jets or whatever, not be the favorite one in the current boundary conditions.
Okay. And do you think that supersonic flights could ever use hydrogen as fuel or even go fully electric?
Yeah, but even if you would go hydrogen, you have that water vapor issue in the ozone layer. So that's part of the problem. So it doesn't solve it. Yeah. And there's limited knowledge what it does mean if you would, let's say, change the combustion process. So for the time being, it's very interesting to look at it, but in a widespread, let's say, part of the air transport system, I won't see it.
Okay.
So one thing that I realize sitting in your lectures is that there's a lot of acronyms that are being thrown around. And I just wanted to maybe put you on the spot a little bit and then see if you yourself remember them. So let's start with an easy one, TSFC.
Thrust Specific Fuel Consumption.
Very good.
That's not still an easy one.
Okay. TLAR.
Top level aircraft requirements.
Yep.
And then this last one, if you get it, I would be amazed. WECPN.
WECP.
Has to do with noise.
That's one of the noise metrics, but I don't know the details.
Weighted equivalent continuous perceived noise level.
Yeah.
So that means I won't expect to see this on the exam.
No, that's a tricky one. No. You don't have to write it. No.
Another thing I think that's interesting for students is, you're obviously a professor. You've made a good career for yourself. But if you were a student studying aerospace right now in this degree, I'm curious as to what your best grade and in one of the core courses, what your best and your worst course would be.
Worst is simple because that's everything related to control.
Okay.
That's quite easy.
So that's why you have Professor Holzappel right next to you.
Exactly. So this is why we are a good team. So the best one is hard to tell. Probably it's either on the engineering mechanics side or it's on the fluid mechanics side.
Okay, very interesting.
Okay, so on to our final questions. Yes. What do you like to do in your limited free time?
In my limited free time, going golfing. We just bought a camper van, so going on tour. Okay. So being on tour. Mm-hmm. Yeah.
And so I guess to finish off, if you had to give a piece of advice to students here at the university or whoever's listening about leadership and being a good leader, how would you say, or rather, what are the good attributes that a leader should have?
Oh, that's a hard one. Normally what you have to do, you have to provide some freedom and also, let's say, provide the capability for the people to do, let's say, self-responsibility in what they're doing and provide them the freedom, but provide them also the backing if there are open questions. So this is always the hardest one, really, to find the balance in there. Let's say to let loose, to let them do what they want to do. Still, you have to be in the loop just to, let's say, capture their back if something is not turning out as it's supposed to do, which might not even be their fault. I guess this is I would consider the most challenging one. So you have to find the right balance in there. And you also have to listen to what your, let's say, personal, let's say, preferences are and how you want to deal with that.
Well, Professor Hornung, thank you very much for joining us.
Was a pleasure.
And thank you for listening to this episode of On Air Actually Rocket Science, and we'll see you next time.